So we started section 2.2 last time. We're taking a look at graphs of other trig functions, and we had taken a look just briefly at tangent. And just to remind you what that one looked like, it looks like the graph of x cubed, kind of, but sandwiched in between, sorry guys, sandwiched in between asymptotes. And of course it has this repeating fashion to it as well. So we saw this one last time. The next one is very, very similar, okay? So the next one that comes is actually cotangent, and cotangent is going to look a lot like this one, but it's going to be flipped upside down. So instead of being increasing arcs or segments, sections I should say, they're going to be decreasing, and it's going to be shifted a little bit, okay? So our cotangent graph looks something like this. We have asymptotes, but they occur at slightly different locations. So let me just sketch in the picture first, just like we've been doing on the other graphs. You're going to have an asymptote here at the y-axis, and then symmetric on either side of it. Put those in as well. The values that are on either side, and this repeats, it continues, right, are pi over 2 and negative pi over 2. And then they'll show up again at 3 pi over 2 and 5 pi over 2 and 7 pi over 2. Halfway in between these are your locations for your x-intercepts. And as I mentioned before, instead of being increasing arcs, they're decreasing. Not really arcs, but sections. Branches is what they usually call them, I should say that. So they look something like this. So they do, in fact, look very much flipped upside down and shifted, okay? These also come from the unit circle. We belabored the point considerably with sine and cosine, so I don't want to do that a lot with tangent and cotangent, so I didn't do that last time, but let me show you what I mean for cotangent. So for x and y, if the x value is 0 on your unit circle, then we're at the positive x-axis. Cotangent is x divided by y. If x is 1 then, and y is 0, 1 divided by 0 is undefined, so we get undefined. So that's why at the origin, essentially, right, the y-axis, you're getting this asymptote happening there, because undefined value. If you put pi over 4, so you're halfway into quadrant 1, excuse me, you have equal x and y values. So they have square root 2 over 2 and square root 2 over 2. And when you divide those, you get 1. If we go all the way up to the top of our unit circle at pi halves, right? Do you have a picture in your mind of the unit circle? I hope so at this point. We've studied it quite a bit. The top of the unit circle, your ordered pair is 0, 1. So now when you are looking at dividing x by y, 0 divided by 1 is 0. So that's why we're getting an x-intercept here. And I don't have it marked, so let me go up here and mark it. This is at pi over 4. And correspondingly over here, it's negative pi over 4. I totally drew that in wrong. Hang on. Yes, those are pi over 2s. That's my fault. I just put my labels are wrong. That's what's wrong. Okay, let me fix those. Okay, the only thing that's wrong here is my labels. I just labeled it wrong. Okay, let me fix those. I should have done it smaller. Okay, let me fix that. The image is correct. I just have my labels wrong. So this is at pi and negative pi. These are pi halves. So sorry. I didn't plot my pi over 4s. That's what was going on. So at pi over 4, we're at 1. So that's right here. And then we'll plot the next one. It's going to be down here at negative 1. Here we go. If I just plot a little bit more, I'd get all the pieces in there correct. So they're at negative pi and at pi. And then after pi over 2, we would go to 3 pi over 4. So 3 pi over 4 is in the middle of quadrant 2. So my x and my y values are the same, except for one's positive, one's negative. And so when I divide them, I get negative 1. And if I go all the way over to pi, I'm at the ordered pair, right? Negative 1, 0. And when we do negative 1 divided by 0, I get undefined again. So we end up at our asymptote being undefined at pi as well. All right, so a few of the details then over here on properties, right? So my domain is pretty much all real numbers except these asymptotes, right? So all these asymptotes are happening at whole pi values, pi over 2 I'm not pi over 2 in pi. So 1 pi, 2 pi, 3 pi, 4 pi, and the negatives. So -1, -2, -3, all those pi. My range is positive infinity, negative infinity to positive infinity, goes all the way, the whole gamut of the y values. It is an odd function. Now this one's an odd function, but it's harder to see than the other ones because it doesn't actually go through the origin. But if you take your paper that you've drawn, okay, so take your paper, and I want you to flip your paper up 180 degrees upside down. Is the picture exactly the same as it was before? It is. So it's an odd function, even though it doesn't go through the origin. Interesting, right? Okay, so it doesn't have to go through the origin to be odd. This one is also odd. Period. The period is pi, right? They're repeating every pi value. So we see from 0 to pi, we have a full branch or a full cycle of our function. Our x-intercepts are actually at the half pi values, so pi over 2 kind of values, all the odd ones, because if you do even ones, then they divide and they become a whole pi. So all the odd pi over 2 values. There's no y-intercept because there's an asymptote there. And our vertical asymptotes, in fact, are at all of the whole pi values, so n pi, and our branches are decreasing. Okay, so the next list is going to look like a list we've already seen before, very similar in fact, but not identical. Guidelines for graphing tangent and cotangent functions. So you'll notice some details about how this is written. This has y equals a tangent bx or a cotangent bx. We've already talked about how the a's and the b's sort of affect things. The interesting thing with a, just to make mention of this real quick, is that if you take the a, it was what we called amplitude for sine and cosine, right? So it took our graph and it sort of stretched it up and down. Does that make sense? We stretched it out of shape. Well, if you take these branches and you stretch them out of shape, they don't change a whole lot. They just don't look a lot different. They can be taller and skinnier, but they're still approaching the same asymptotes. They're maybe doing it faster or slower, but they don't really change a whole lot. So the a value changing doesn't really affect the graph. The b value can, and does, right, if there's a b value. So b affects the period. So our period is typically 2 pi for sine and cosine, but it's pi for tangent and cotangent. So what you see happen here in your notation for period is that instead of doing 2 pi over b, it's just pi over b. Because the period for these graphs isn't 2 pi, it's pi. You also see what happens when you're looking at finding those asymptotes. So this is almost like what we did when we did phase shifts, right? When we did phase shifts, we stuck the ending values for this triple inequality between 0 and 2 pi. What you're seeing happening here is just the locations being between an asymptote. So you can get one full cycle on tangent if you go between negative pi over 2 and pi over 2. And you can get one full cycle for cotangent if you go between 0 and pi. So that's where these are coming from, is these are the asymptotes that correspond with the function tangent, and these are the asymptotes that correspond with the function cotangent. That's where those are coming from. And then once we find those values, we can actually sketch those asymptotes. That's step 2. Step 3, we're going to divide the interval in half. That's the only one we're going to label is the asymptotes and the division in half. The division in half spots our x-intercept, so we're going to label the x-intercept. And so it says that middle value where we've divided it. Number 4 is this x-intercept. And then on 5, we're going to use that x-intercept and the asymptotes to sketch the graph, and we will draw additional periods if we're requested to do so. And I do believe we're going to be doing some additional periods today on these graphs. We haven't seen that happen just yet, but we will. Okay, that slide's a lot. A lot of those details are very familiar, but slightly different, right? Because we're working with different trig functions. And we're going to take a look then at some examples. Okay, is anyone still needing to write down from this slide? I'll pause if we do. Still a couple people still writing, so you keep writing, it's fine. Okay, are we okay to move forward? You good? You good? Okay. All right, so let's take a look at an example. Our first example is an example that's cotangent. So let's actually just move a little bit from left to right on these. So notice the first thing here is that there's a negative here. What happened with sines and cosines when we had a negative in front? Do you remember? It flips over the x-axis. Very good. So I'm going to make that and sort of note to myself to remind us that when we graph it, we have to take that into account. So this flips over the x-axis. All right. Even if there had been a number in front, we don't have to do anything with it. It's not called the amplitude. It doesn't affect the general shape, so it's not something we have to contend with here. That's good. We do have to contend with the 3 that's inside. All right. So it's going to affect the period here. So the period is going to be pi over 3. And we're going to set up our interval using the cotangent asymptotes. And the cotangent asymptotes are 0 to pi. So you'll see that 3x in the middle, and you'll see that 3 coming through. It seems a little bit unnecessary for this one because it's cotangent. But when we deal with tangent for doing this, setting up that interval is going to be even more helpful because tangent spans through the origin. And this one's just strictly on the one side or the other. So it's not quite as necessary. But here's the way that this would work then. Okay, so you're going to draw a graph. It tells you that you're going to have, these tell you asymptote values. I mean, that's what these tell you. These are some of the asymptotes that we're going to have. So we're going to take a look at drawing asymptotes at 0, that's the y-axis, and at pi over 3. And I'm going to draw my asymptotes in a different color just to distinguish them. I'm going to use green. So we're going to have an asymptote, hang on, happening, and I'm almost doing it to the side of it just so you can see it better. You can kind of see that green showing up. And there's going to be one over here. And the value on the right-hand side is going to be at pi over 3. Okay, does that make sense so far? We're just going to do one period first. We need to split that interval in half. So what is halfway between 0 and pi over 3? Pi over 6. Very good. So we're just dividing. Okay, so if you're not sure where that came from, we took pi over 3 and we divided it by 1/2, which is the same thing as pi over 3. Sorry, I meant divided by 2, which is the same as times 1/2. Let me rewrite that. Divided by 2, which is the same as pi over 3 times 1/2, or pi over 6. That's what's happened here, okay? So that's halfway. It's pi over 6. And I'm going to draw the x-intercept at that location. So my x-intercept is right here at pi over 6. Okay, pretty good? Now, how does the cotangent graph typically look? Is it increasing or decreasing? It's a decreasing graph. Is this one going to be decreasing, though? No. How come? Because it's flipped, right? So we have to pay attention to what it typically does, and in this case, reverse it. Typically decreasing, but this one's going to be increasing. And when it does that, it ends up looking like tangent, right? I mean, like, that's what happens when we flip this puppy over. Like, that's not a surprise. Now, you have a choice. This one says to draw this over 2 periods. You can draw an additional period to the right. There's nothing wrong with that. Or you can draw an additional period to the left. There's nothing wrong with that. You get to pick. My suggestion, at least with cotangent, is to draw it to the left. And here's why. All those values we just found are going to be the same and negative if I do it on the left. I don't have to find anything else, right? Because of the symmetry that's being involved. So I can draw my asymptote over here. And I can label that this is at pi over 3, negative, and this is at negative pi over 6. And I can just draw in the same pieces that I drew before. So I almost, with cotangent, this doesn't work like this with tangent, but I almost with cotangent get this for free if I do just the left-hand side instead of increasing values on the right-hand side. Okay, cotangent is the easier of the two to draw. That's why we started with it. Okay, you ready to take a look at one that's tangent now? Of course you are. Let's do it. Okay. So moving from left to the right, 1/2. What do we need to do with it? Somebody tell me. What's it? What do we need to do with it? Well, it was the amplitude when we did it with sine and cosine. So nothing. You wouldn't need to do anything with the 1/2, right? We're going to rather ignore it. Does it change the shape? Slightly. Is that really relevant because we're just sketching? No, not real relevant, so we don't have to worry about it, okay? The rest of it, though, we do need to worry about. So there's a 4 right here. So if I wanted to find the actual period, I could do that. I will write that in so you can see it. The period should be pi divided by that value 4, so the period is pi over 4. But with tangent, that's not real helpful because tangent has to have this pi over 4 period spanning to the left and to the right of the x-axis. Okay? Could you use it and go from there? You could. So if you look at that and you're like, well, I know how to use that from there, that's great. Another option, though, is to take a look at that the way we said with phase shift. So the period is typically negative pi over 2. These are also strictly less than signs. I don't know if I wrote that right on the previous slide or not. Let's see. I did not. The reason they're strictly less than signs is because we actually have asymptotes at those values. They are strictly less than signs on the actual guidelines. Okay, so on this then, we've got typically negative pi halves to, and I did it again, to pi halves. Okay, and then we're going to divide by 4. And dividing by 4 is the same as multiplying by 1/4. So this ends up being negative pi over 8 to pi over 8. Okay, is that all right? Okay, so drawing one period, we can get directly off of that piece of information. I have an asymptote on the left, and I have an asymptote on the right, and these values are at negative pi over 8 and pi over 8. And I don't even have to worry about what's in the middle. I know what's in the middle. It's the origin. That's great. This is a graph of tangent. Does tangent increase or decrease? It increases, and hence it looks like this. And if we just had to do one period, we'd be done. But it says 2, right? So we need to do an additional period. And we can choose to the left side or the right side, but it's going to be the same thing. I'm just going to move to the right side. That's what I think we would typically see happen. So we'll go with that. So now I actually have to figure out what those values are. There's 2 more values in particular I need. I need to figure out what the asymptote value is at this green asymptote that I've drawn. And I need to find out what the middle point is right here. Okay, are you with me? And this is going to involve some fractions because there's fractional pieces that are going on. So that part's not super friendly. But I have pi over 8, and I need to be able to get from pi over 8 all the way over here. And what is the value of my period? Like, how far apart are they? What did it say? It's pi over 4. So it's pi over 4 to get from one green asymptote to the next green asymptote. So I need to take the pi over 8. I need to add a pi over 4 to it. Once we do one, you're going to see a pattern on this particular one that we may not have seen before, but it is there. I need to have our denominators be the same, so I'll do that, or you can use your calculator to find them. That gives me an 8 on my denominators. I have 1 pi then and 2 pi to give me 3 pi over 8. So this is 3 pi over 8. So if the first asymptote was pi over 8 and the next asymptote is 3 pi over 8, what's halfway between? 2 pi over 8, which is the same as pi over 4. Okay, halfway between, we have 1 pi and then 3 pi. Halfway in between is going to be 2 pi. So 2 pi over 8 is this location in the middle, which is the same as pi over 4. So pi over 4 is right here. Okay, so we have to work a little bit to get those pieces. We didn't have to work on those pieces when we did cotangent. We'll plot the value in the middle, and then we will draw increasing branch. Okay, so you may have not thought about it when I did the guidelines, but when I did the guidelines over here, I didn't change or have the option of what happens inside here when there may be addition or subtraction. Did anybody notice that? Okay, so it's intentionally left off, not because we're not going to do it, but because it works exactly the same way, and it just sort of makes a mess of all of the details if I put too much on the slide. So I wanted to show you one with an example so you can see that it does in fact work the same way. So this one does have a shift, right? How do I know it's a phase shift? Because there's addition and subtraction inside with the angle x. Okay, it's affecting the angle. There's going to be a shift going on. The shift is a horizontal shift or a phase shift because it's happening inside with x. Now, this is still tangent. We just did one with tangent. We know that our interval endpoints based on our asymptotes go from negative pi over 2 to pi over 2, right? Okay, it's going to be the same thing, just like it was when the period was affected. This one's the phase that's affected. And in between, we're going to put the x minus pi over 4. So our goal, just like before, was to solve for x. So what do I have to do? Okay, so I know I've been kind of doing a lot of the detail work for, for the addition and subtraction of fractions. We're going to start doing less and less of that. If that's a place where you're struggling, this is one of those places you should probably come and get some help. Fractions is a long time ago, I know that. But it is a place that I don't want to spend this amount of time moving forward. Jess, do you have a question, Braden?
Is the left and right side always -2?
It is for tangent. Yeah, so it's always negative pi over 2 and positive pi over 2 for tangent. When we're working with cotangent, it's 0 and pi. Yeah. Okay, any other questions? Okay, so either with your calculator or with your skills with addition and subtraction with fractions, what is negative pi over 2 plus pi over 4? It is negative pi over 4. I have x in the middle. And then what is pi over 2 plus pi over 4? It's 3 pi over 4. Okay, so the difficult part of this particular one drawing is that it's no longer symmetric. So when I draw my asymptote on the left, it's going to be much closer to the x-axis, and not x-axis, the y-axis than it was before compared to the one on the right. So if I draw it in right here, right, the other one needs to be over here. And the reason is because this value is supposed to be at negative pi over 4, and this value is at positive 3 pi over 4. They're not symmetric any longer around the y-axis. It's been shifted. And the halfway point is no longer the origin either, right? So we would need to know what is halfway between negative pi over 4 and 3 pi over 4. So if we were to add those together, negative pi over 4 plus 3 pi over 4, and then divide by 2, do you know what you get? We get pi over 4. And again, you might be able to look at that and see that from the perspective of a little bit of patterning, right? If I'm going from negative pi over 4 and I'm making equal sort of interval moves, it's 2 moves to the middle. You know, if I go through the origin here, I go 0, and then I do pi over 4, and then I do pi over 4, 2 pi over 4, 3 pi over 4, something like that. Your calculator will also do the addition. We can talk about details if you need them. This is a graph of tangent, so that's my x-intercept. Increasing or decreasing for tangent? Increasing. So this is my branch. But again, I have to work a little bit more to get the next one. So I'm going to move over here to the right. So I need 3 pi over 4 plus the period, and the period is pi because nothing affected the period in front of x. The period is still a full pi. So when I add 3 pi over 4 and pi together, thank you, 7 pi over 4 is what I get, yes. And halfway in between them, you can probably identify in terms of patterns at this point. These are all odds over 4, right? So I have 3 and I have 7, halfway between would be 5. So this is 5 pi over 4. Increasing branch so that it looks like that. Okay, how are we doing? Are we okay? Okay, we have two more graphs. What are they? Secant and cosecant, right? And the issue with secant and cosecant is that you're not going to get a whole lot of details because you actually already have them all. So a secant graph. So recall that the secant graph, or that the graph of cosine, y equal cosine x, the x-intercepts at the graph will end up being vertical asymptotes of the reciprocal graph y equals secant x. So remember that secant and cosecant are reciprocals. So the maximum points will become minimum points and vice versa. So I'm going to sketch you the general graph so you can see what this is referring to. And you definitely are going to want to use either different colors, if at all possible, or something like that to be able to draw it for yourself. So the graph of cosine, and I'm not going to label lots of things. I'm just going to show you what the general image looks like because that's the goal on this particular point for me. So our graph of cosine typically starts at a what? Peak or at x-intercept? It's a peak. It's a peak, and it comes down here, and then it comes down, and then back up, and then back up, right? Okay, for the purposes of drawing, I'm going to actually go down on the left as well because it'll make it easier for my sketch that I'm finishing out. And I want to draw two periods just so you can see the full picture, maybe in more than one image. So we're going to go down again on the right, and down. And then we're going to go back up and up. And these are, of course, all supposed to be equally spaced out. They're not perfect, but I hope it gives you a pretty decent idea. So my graph of cosine generally looks something like this. That's not good. Try that again. Okay. It's not perfect. It's actually getting a little wider on the right-hand side. Sorry about that. But are you getting the picture, right? Like this is not anything you haven't seen before. It is a little bit weird that I maybe went over here on the left-hand side when I don't normally do that, but here's why. What it actually just told us is that all of the x-intercepts are x equals zeros. And when you do a reciprocal of something that's zero, you get something undefined because the zero comes to the denominator. So all these x-intercepts actually become asymptotes. I think that's probably far enough. I didn't need to draw the extra at the end. That's okay though. All right, and then all of the peaks become valleys and all the valleys become peaks. Maximums and then become minimums, minimums become maximums. So I'm going to draw my graph in yellow. We'll see how well this shows up. So this point right here was a peak and it's now a valley. Instead of it being contained and going like this in this wave pattern, instead, these are branches that open up and branches that open down. So they end up looking like this. And this branch at the bottom opens down like this. And then there'll be a branch at the top opening up like this. And a branch at the bottom opening down like this. And the pattern repeats. They kind of look like parabolas, but they're not because they're trapped, right? Kind of like that x cubed looked like our trig function, the tangent one, but it's not because it's trapped. But it has that same sort of feel to it, right? It's got a peak, it's got a valley. Notice the domain for this is sort of the reverse of what we had from before, not domain. The range for this is the reverse of what we had before. The range for my white graph, by the way, let me label them. The white one here is y equals cosine of x, and the yellow one is y equals secant of x in yellow. So the cosine graph, its range was trapped between -1 and +1, right? But the secant graph isn't there at all. The secant graph goes -infinity all the way to -1, where it stops and it jumps up to 1 and then goes up to infinity. That's what its range does. And in the very same way that this happens for secant, it also happens for cosecant. Okay, so all the same details that you just wrote down is what you're going to write down again on this same slide. And I'm going to sketch the same graph, and this one's actually a little easier to sketch because I don't have to span over to the negative side of the x-axis. So the sine graph typically starts at the origin, right? And it goes up, down, down, up, up, down, down, up. Again, eyeballing it. And I'm going to sketch that in for the sine graph. Okay, that look okay? I mean, ish. Okay, all the x-intercepts are going to become asymptotes. The graph that I drew in or wrote in white is y equals sine of x. And then I'm going to use yellow, and I'm going to create the branches that open up and down from there. And these yellow branches, all of them are y equals cosecant of x. It feels like same song, second verse, right? So I don't really need a whole bunch of new rules to graph secant and cosecant. What I actually need is to draw the graph of sine and cosine, whichever one it goes with first, and then I automatically get the other pieces for secant or for cosecant. Okay, so these are actually called guide curves. Your sine curve is a guide curve for cosecant, and your cosine curve is a guide curve for secant. Okay, so when it refers to guide curves, that's what it's talking about. It's talking about the reciprocal one that we've got all these details about how to graph. So here's our guidelines for graphing. So graphing for our secant and our cosecant functions, the graphs of y equals a secant bx or y equals a cosecant, that's a typo, that should say cosecant. CSC bx with b greater than 0, follow these steps. First, you're going to graph the corresponding reciprocal function using it as a guide. You can sketch it in pencil. So if all you're working with is pencil, that's great. If you don't have any colors with you, you can sketch it with pencil. Or you can change it to a different color, right? So if you have a pen or a colored pencil with you or something like that you want to use, that'd be great. And you're going to label the curves. You do need to label what you've done, okay? So especially if you are using different colors, like if you're using red for secant and you're using yellow for cosine, I need to know which one's which, or at least I need to know that you know which one's which. You're going to sketch the vertical asymptotes from the guide equation, x-intercepts, in a different color. So again, you're going to use a different color. And you're going to sketch the U-shaped branches above / below the guide curve in a different color. Okay, so you're going to use some kind of different colors or some kind of a different way that you're marking these. Very bare minimum, asymptotes are always dotted. Okay, even if you don't have a different color, you should at least be able to dot them. And your guide curve is either dotted or it's in a different color that you label. Either way, you're going to label. Okay, so I'm going to use different colors because I have abilities with the iPad to do that very nicely. So we're going to do an example, number 4. So we have 2 cosecant of 1/2 x. Directions say to graph each function over a 2-period interval. So we're going to all hope that you get to do some 1-period intervals as well, but I want you to have some practice with some 2-period intervals with these. We're not going to have to label near as many points either with these. Okay, so when we were doing sines and cosines, we were labeling a lot of values, weren't we? Yes, this is yes. We were labeling lots of things. We're going to label a few fewer things on these. All right, so to start with, we have cosecant of x, or cosecant of 1/2 x. So what is the guide curve that we're going to draw first? Sine. So the first thing I'm going to do is I'm going to change this. I'm going to change this into y equals 2 sine of 1/2 x. Okay? Flat out changing the equation because I'm going to draw that one in first. So some features of this function, we do have amplitude back in the right. Amplitude, 2. And what is my period? Well, my period should be 2 pi, because that's normally the period for cosine and sine. And then it's divided by the coefficient in front of x, which is 1/2. So what is 2 pi divided by 1/2? It is 4 pi. Very good. It's not 2 pi divided by 2, it's 2 pi divided by 1/2. It's 4 pi. Okay, is everybody good so far? Fabulous. So we're going to go to a graph now where we need to have a cosecant curve, or I'm sorry, sine curve first. It has to start at 0, and it has to have a full period by the time I get to 4 pi. And I don't want to go all the way to the edge because I need to do 2 periods worth. So here's to 4 pi. And then if I double that, I'll be at 8 pi. Does that make sense to everyone? So far, so good? Good, good. Okay, we do need a halfway point here to be marked. So halfway between 0 and 4 pi is 2 pi, and halfway between 4 pi and 8 pi is 6 pi. Those are the bare minimums you need to mark. And then you also need to mark the amplitude. It's happening at 2 and -2. Now, we're going to mark the locations. We're just not going to write in the values that are halfway in between. So this sketch will be better than the sketch that I did before because I didn't mark anything out, right? I just kind of eyeballed and put dots. Sine curves. Where do sine curves start?
Origin.
They start at the origin. So this graph will also start at the origin. Where does it go next? It goes up to 2, and then it's going to go back down to the x-axis, down to -2, and back up to the x-axis. This is a full period of sine, roughly anyway. And then we're going to repeat it, right? We're going to go up to 2, back to the x-axis, down to -2, and back to the x-axis. And try to smoothly connect it as much as we can. And we're going to label that this graph is the sine graph. We're labeled with a whole value. So it's y equals to sine of 1/2 x. That's what this graph is. And mine's in white. So I'm going to continue to do my asymptotes in green and my other graph in yellow since I've already established that. So asymptotes occur where? All the x-intercepts. So at every x-intercept, you're going to go in and you're going to put an asymptote. If you don't have any colors, make sure at least you're doing them in dotted. If you're using a calculator to support you in your sort of homework and thinking about these, that's okay. Just recognize your calculator is not going to draw in asymptotes for you. It's just not. It's going to either try and connect things or it's just going to leave them completely off the screen, but they need to be drawn in when you sketch it, okay? And then we are going to draw the branches. So all of our maximums and minimums create the location that's sort of like well, it's a peak or a valley for our branches. Looks like this. And then these yellow ones are actually the one that's y equals to cosecant of 1/2 x. Okay, how are you feeling? Is that okay? I feel like cosecants and secants aren't hard to draw because they're already building on something that we worked a lot of time. I mean, like section 2.1 was a long section. I mean, it literally took 2 class periods, pretty much, right? I mean, almost all of 2 class periods to really get through that section of material because there was a lot in it. But now that we've done that, we can build on that, and the next 2, cosecant and secant, because they're reciprocals, we get them not exactly for free, but at very little cost to us because we've paid a high price already. Okay? All right, let's do one more. Secant. Nothing would be complete without having done all 6 of them, right? Of course not. Okay, so what is the reciprocal function, the guide curve that we're going to be doing? Cosine. So it's got a negative at the beginning. We've got the cosine, and we have x minus pi over 2. Now, there's lots of things that we need to deal with that are different than we dealt with in the previous one on purpose. The first is the negative. What does the negative tell us? Flip x-axis. Reflection is a more accurate term, so if you see that word used instead, keep in mind it's the same thing. This tells us there's a what? A phase shift. Now here's the deal. This is cosine, right? Our cosine graph actually, well, always when we look at our phase shifts for sine and cosine, we go between 0 and 2 pi, correct? Okay. Now that's an incomplete picture from what we had done because I actually, with cosine, when I did this before, I scooted over into the negative side of the axis to get my other value. So keep that in mind. We're going to have to take a look at that when we do that. But we can still set this up 0 to 2 pi. I still have my x minus pi halves between. And how will I solve for it? Fantastic. Add my pi over 2. The left side's lovely. That's pi over 2. The middle is x. What is the right-hand side? It's 2 pi plus pi over 2. It's 5 pi over 2. Okay, so we're going to come over here. We're going to draw this. The graph needs to start at pi over 2. And it needs to have a full cycle out to 5 pi over 2. And then I should have another full cycle out from pi over 2 beyond, right? So what would be the value if I take the 5 pi over 2 and add another 2 pi to it? It would be 9 pi over 2. Okay, is that okay for everybody? Okay, great. And we're going to cut them in half. So what's halfway between pi over 2 and 5 pi over 2? 3 pi over 2. Notice the patterns. When they're there, they're helpful. And what's halfway between 5 pi over 2 and 9? That would be 7. Good job. Now, here's where things get a little wonky. Cosine typically starts where? At a peak. Oh, we didn't write the amplitude. Our amplitude's just 1, so let me draw those in. My bad. Okay, so our normally starts at a peak, right? But this had a reflection, so it's going to start at a valley. So at pi over 2, I'm actually down here beneath the x-axis. And I didn't mark them, but let's go ahead and mark those halfway points to get our points labeled. We don't have to label the values. We're just going to mark the locations. So we're going to go up to the in-between value. We're going to go up to 1, back down in between to the x-axis, and then back down to the minimum. Up to the x-axis. Hang on. My minimum's a little bit different. Let me get that better. Back up to the x-axis, and then back to the maximum. And then back down to the x-axis and back to the minimum. Now, let's connect them. Okay, if I draw my asymptotes in now, they're going to cut through right here and right here, this one, and this one. Okay, let's label our curve that we did here in white as y equals negative cosine of pi x, rather, minus pi over 2. And in yellow, I'm going to draw the other pieces. Now, this maximum right here will be a minimum opening upward. The minimum will be a maximum on the second branch, and I've got my third branch here. So what do I do on this piece on the left, this little half piece over here, and this half piece on the right? We have a couple of options, okay? One option is you can just draw in the half branch that goes here. This is not a super desirable option, but it is an option. This is a full 2 periods. Okay, I mean, you can do that. The other thing that you can recognize is that these graphs will continue, right? So this white that ends at 9 pi over 2 here to negative 1, it's going to go back up, right? And you can figure out what that value is it goes back up to, and you can actually complete the image that's there. Right? It looks like that. So how could I figure out what value it goes up to either on the right-hand side or on the left-hand side? You'd add pi over 2. How do you know it's pi over 2? You're right. You don't know? You're just guessing?
No, I know, right?
You know you're right, but you're not sure how. Okay, that's all right. So if you take a look at what's happening here, we didn't label them, but what was this first asymptote location, this first green asymptote? Can you tell what it's at? It's at 2 pi over 2, which is pi, right? So this is pi over 2, and then we went 3 pi over 2. Halfway between would be 2 pi over 2. This is pi. What that means is that the distance between each of my points that I've plotted is actually pi halves. So this actually at 0 is the location where this graph would come back up to. Now, will they all work out that way? Well, no, they won't. But on this one, it's pretty friendly. They're all pi over 2 spaced apart. So you could actually start over here like this and check it out. If we had taken a look at this from that perspective, oh, can I draw this here? this graph, if you were just given that graph, you probably would not think, hey, this is a cosine graph. What does this graph, the one that's white in the middle, look like? It looks like sine, but not exactly. What does it look like regarding sine? It looks like sine flipped upside down, doesn't it? Sine that went down first. We talked about that last time. Sine and cosine are just phase shifts of one another. So this happens. So don't get all weirded out by the fact that you're like, no, wait a minute, I didn't have a cosine graph, I had a sine graph when that's because it had a phase shift. Okay, that's going to happen. And in fact, this phase shift is exactly what we saw happen in cofunctions back in chapter 1. All right.